Welcome to Unlocking QP, 5 design and coding tips for your QP-based firmware. My name is Matthew Eshelman, and I am an early adopter of QP. I've been dealing with firmware and embedded software for about 30 years, and at least I believe we're at 20 years now of QP, having adopted it from that very first edition book that Mr. Samick put out. I love consulting on QP-based firmware projects. It's one of my favorite things to do. I can help your team adapt their firmware or start a new firmware project based on QP and help keep them out of the weeds. That's what I enjoy doing. You can learn more about me at covemountainsoftware.com. So let's go straight into tip number 1. Tip number 1, to go faster, slow down. Slow down a bit. What do I mean? Well, I mean we have to learn our tools. We have to learn our framework. We have to understand the language we're using, the IDEs we're using. And so in the context of QP, let's read the manual. Let's buy Samick's book and let's peruse it. But what I'm going to go ahead and give you is what I would consider the bare minimum of what you need to read in Samick's book to allow you to get started on your QP-based project. So Chapter 2, we really want to get into that crash course of UML state machines. If you're not already familiar with state charts, UML state charts, this will be very important to you. In particular, go check out Figure 211, which shows many of the transitions that are possible in QP with QP's hierarchical state machines. Build that example, play with it. Just get a feel for all those transitions that are possible. You're going to need to understand those and have them in your toolkit as you're developing code for your firmware project. And then check out Chapter 4, where we get into some of the details of QP's hierarchical event processor. And we want to check out sections 4, 6 for the exact steps, the common steps for implementing your hierarchical state machines, which are the core of your active objects in the QP framework. And then we definitely want to take a look at section 4, 7, pitfalls, common mistakes people make. And then I really want you to sit down and read Chapter 5, State Patterns. There are multiple good patterns in there that you need to be aware of so that those tools are in your tool chest when you're going to design and write the firmware using QP. Especially things like the deferred events, transition to history, those. At least one of those patterns mentioned in Chapter 5 is going to be used in your project, and in any real-world project. So take a good look at that chapter. And then, when you're done with that bare minimum, peruse the rest of the book and zoom in, zoom out. See if you really would like to get a master's course in the many, many decisions that went into creating a framework like QP. Then there's a wealth of material to read and learn from in this book. So that is tip number 1, read the book. Okay, let's discuss tip number 2. Tip number 2. If I can get the mouse on the correct place. Tip number 2, background. So QP projects, everything in QP is event-driven, ideally, meaning something happens and it sends a signal, perhaps with some associated data, to an active object which implements some sort of state machine, and that event triggers some behavior, typically a state change or some sort of code execution. All of our events are distinguished by enumerated signals, i.e. numbers, integers. So every event needs a distinct, unique integer value, enumerated signal value. And what you'll find when you get into QP, and this sometimes trips people up, which is why it's a tip. It's going to seem like a kind of trivial tip by the time we're done, but I've seen this cause confusion on multiple projects. So a little more background though. So what we end up with in a typical project is we end up with these kind of logical groupings of signals. QP obviously has some reserved signals, and these are terminated with Q user sig, and that's where your project's signals start. And typically, I'd say it's basically required, your pub sub, so signals, events that can transition or that can transit the publish subscribe framework, we start those with Q user sig, and then we always make sure to note the final signal in that range of signals. This is important in particular because when you're using the publish subscribe features of QP, we're going to end up allocating an array and giving it to the framework so it can track who is subscribed to which signals. So this portion of our signal enumerated list must be clearly designated, and it's generally best to start it at Q user sig so that we keep that max value as low as possible for RAM allocation purposes. Then typically, not always, but typically, a project will have a number of events that are posted directly. So one active object just posts an event with an associated signal directly to some other active object, and vice versa. So we have to enumerate all of those signal values as well. And you'll notice we have a max posted signal. Then each active object, traditionally and typically, has its own private signal values. These are frequently used for timers and maybe deferred event handlings, just different things that the active object may post to itself or has the framework post to it, such as timers. And we notice here, since they're private and we have multiple active objects and they're all keying off that max post signal in this example, those signal values are going to overlap. And that's fine as long as they don't get posted for some strange reason directly to another active object. And this is where the mistakes start to happen. This doesn't, if you're just a 1 or 2 person project, these type of mistakes probably aren't going to happen. But in the larger projects that I've been involved with, several things happen. Somebody keys their private signals off the max publish subscribe signal instead of the max post signal. So now their private signals are overlapping with the posted signal values. Or for some strange reason, somebody doesn't protect the privacy of their signal, and it ends up leaking and becoming a directly posted signal. And what ends up happening is that you get a very confusing bug where you swear you're posting, private A sig, but some other active object is processing post A sig behavior. And again, this is just human error, but I like to avoid human error. And when your projects get larger, you really want to kind of go out of your way. So what is my tip? It's going to perhaps seem trivial, but I want us to use a distinct enumerated signal value range for each active object. So let's just go ahead and reserve our pub sub signals up to perhaps 999, just as an example. You still need to track your actual max because we don't want to allocate memory for 1,000 pub sub signals yet. But let's just reserve that entire range. And then each active object would then get assigned a range. You could track this in a header file, or you could just put it in your documentation, and each developer would need to adhere to it. But the foo active object in this case is only allowed to use 1,000 to 2,000, or 1999, so the 1,000 range. That includes the posted signals that they define, which would be any event that they can have posted directly to them, or if they define the response to that, that's also directly posted, it would define all of that. And then after it's defined posted values, it could then key off whatever the maximum of that range was and define the rest for private. The beauty of this is this is also one of the other benefits, is if you're not using QSpy or for whatever reason, or you're just using printf, or you have some other logging framework and you're just %d printing that integer of the signals of the events that are coming in. If you see a 1010 value, you know it has something to do with the foo active object, for instance. So this helps the humans from a debugging point of view. It helps the humans from a preventing mistakes point of view. And then each active object would get a block of 1,000 or however you want to do it for your project. And again, this is all about avoiding mistakes, and in a debugging scenario or where you're logging with printf or some other logging mechanism, just making it just a little easier to know which active object that signal belongs to. And one last point on tip number 2, with these defined ranges, you can also use the wonderful static asserts to ensure that you don't accidentally overflow your assigned ranges. So that'd be yet another tip to toss into this tip number 2 bucket, is enforce these ranges using static assert. Tip number 3. Number 3 already. Tip number 3, let's follow a basic software architecture, or at least consider this as you are coming up with and designing your first QP firmware, and trying to understand what do we mean by active objects and how should we treat them. So here's what I would recommend. We're just going to typically end up with a 3-layer architecture. So at the top is our director, our executive, the main app, whatever you want to call it, the boss. This is a single active object that has our top level product state machine. This is the active object, and this is the state machine associated with it that you're probably going to be able to most directly trace to, for instance, a user manual. So the states that we read in this director state machine should be almost one-to-one with chapters or sections in a user's guide for our product. This is the top level behavior. This is the boss. This is the active object that's in charge of our system overall. And in that vein, we need to think of the remaining active objects entirely as services. And what do I mean to that? They don't do stuff unless they are told to do stuff. They act as directed. And I think I would recommend, even during your initial startup of all your active objects, all your services, I want our service-oriented active objects to even do almost nothing during their initial startup, because I want the director to decide the order of events on that critical startup behavior of our product, our device. This is perhaps just historical for me because I spent 10 years working on digital television embedded software, where we were benchmarked on how fast that television could boot up and get showing the customer the video of the channel or the input that they were last looking at. So we don't want to just have all these services willy-nilly doing whatever the heck they want when they start up. Ideally, we want the director to say, okay, service A, you can now do your initialization. Okay, service B, you can now do your initialization. So really think of these as services that need to be told what to do. Now, that could be a broad-based action like, hey, GPS service, start, do what you do and just emit coordinates from time to time. Thank you. So, the director, we don't want it to be a micromanaging director, but we do want it to be in charge. And then all these services, so the director only talks to services, ideally. It doesn't talk to any hardware as much as we can get away with that. These services are directly tied to one or more drivers each. But at this point, if we're going to a QP framework, we need to really take a look at the drivers we're going to be using. We need to embrace the async. We need to embrace asynchronous behavior in our drivers. This means no busy loops. This means no sitting spinning on a register looking for a bit to go from 0 to 1. Let's not do that. Let's use our interrupts. Let's use as much as possible fully asynchronous behavior so that our services aren't blocking on, or aren't sitting and spinning on anything. In a typical QP project, we can't even block on anything if we're using one of the strict run to completion kernels. So we really want to embrace the async. If we're going into the QP world, we embrace the async, embrace event-driven software, and let's let our drivers reflect that reality as well. Tip number 4. Time for tip number 4. So, as we sort of alluded to briefly on the previous tip, we have different kernels to deal with. QP is a framework, and it runs on a plethora, you can choose all kinds of different kernels. You can choose QPs from among QP's 3 different kernels, or you can choose from other kernels. So how do we make this decision? What I've come to the conclusion is the primary way to help guide you in making this decision, in selecting a kernel, is to understand and review any third-party libraries that you will have to use in your product. So let's make sure we understand our different kernels real quick then, and then we'll talk through this. So QP gives you 3 different kernel choices. QV, which is almost like a super loop, where a active object, when it starts processing an event, it is never preempted until it is done with its processing. Then the kernel takes over and takes a look around, and if there's a higher priority active object that has an event waiting for it, then it gets CPU, et cetera, et cetera. So it's a non-preemptive kernel, and that is going to be the easiest kernel to understand from a real-time analysis point of view. Then we have QK. This is probably more along the lines of what many of us are used to, a preemptive real-time operating system kernel. And QK and QV, both of those, in your active objects, you have no way to sleep, no way to lock a mutex, no way to wait on a semaphore, etc., etc. The kernel and the underlying active objects deliver your events to you, and that's all you care about. And that's additionally all you actually can do. Then we have QXK. QXK is the same as QK. So when you're in an active object context, it looks exactly the same as QK. But we've added these raw extended threads. And when you create an extended thread, that's not an active object. It's more of a traditional thread, real-time operating system thread. And when you're in that context, now you have semaphores, mutexes, queues you manually deal with, or the ability to sleep the thread for a certain amount of time. And then on top of that, QP provides porting layers for various well-known operating system or real-time operating systems, such as FreeRTOS, ThreadX, POSIX, etc. So how do we make this decision? Now we have multiple choices. And what I would tell you then is take a look first at all of your third-party libraries that you're going to use. So for instance, let's say you need to use a certain TCP/IP stack, and that stack is tied to FreeRTOS, and that stack has no porting layer. And when you go look at the code, it's just scattered around spaghetti. And we find, semaphores and mutexes and queues, oh my, and all over this TCP/IP stack. And for some reason, you have to use this particular stack. Well, if that's where I'm at, then I'm just going to go probably just use FreeRTOS, period. Oh, and I forgot to mention, if you choose one of the third-party operating systems, such as FreeRTOS, then your active object can violate the strict run to completion. Now you can, pinned on a semaphore in the middle of processing an event. We don't want to do that, ideally. Let's do our best to adhere to that strict run to completion approach to writing this code, because that does result in more reliable, better software. But now you've lost that safeguard that the QV, QK provide if you end up choosing FreeRTOS. Beyond that, so on another project, for instance, a semiconductor company provided library for a complex piece of hardware that we needed to use. It had a porting layer, and when we looked at it, all it needed was a semaphore and some sleep. So it was very easy, and we ported it to QXK. So we ran that semiconductor library's code exclusively in an extended thread, while active objects controlled and messaged, sent messages to and from that thread. That worked out great. If all of the code is 100% in your control, then I would tell you use QV or QK, depending on your needs. And, a simple, easy way to perhaps think about QV versus QK is your typical product that has a user interface where there might be a lot of pixels that have to get rendered. You're going to want QK so that the time-consuming activity of rendering text or whatever it is to your screen can be preempted by whatever is your real-time activities for that product. So that is, I think, everything I needed to say on tip number 4. Again, we have a lot of choices: QV, QK, QXK. Let's try hard to choose QK or QV. But to make that decision, let's take a close look at all the third-party libraries that this product must use. All right, tip number 5. Be wary of exit state behavior. If you've actually followed my blog, you might recognize this. This is this is a past blog entry on my website, so feel free to read about it in more detail. So what am I talking about? So let's take a look at an example. If we take a look at this state, behavior foo, and we see that in the entry, they set an LED pattern to pattern A. And then in the exit state, we have a set LED pattern normal. And that's what I want you to be wary of. Setting the pattern to LEDs is setting the state to something that is visible to the end user or maybe to some hardware. And I'm not saying don't put behavior in the exit state. That's clearly not my advice here. But we do need to be wary of our exit state behavior. And I'm bringing this up in these tips for this video because I've seen people do this and make this mistake in multiple projects, and it creates maybe just a little naggy bug, or perhaps it can be far worse than that. But we want to be careful about the behavior we have in our exit states. So let's take a look at this example. We enter, we set that pattern to A, set LED pattern to normal on the exit. Well, that's all fine and good and dandy. In this example, everything's going to be just fine. But then we come on and somebody ends up adding another state. So now we have foo and we have bar. And we notice both of them are, somebody probably just copy and pasted some code. And we did remember to change set LED pattern to this new pattern B in the behavior bar state. And in both cases, when we exited, we set the pattern back to normal. But you'll notice we have this button B pressed behavior where we transition directly from foo to bar. And if we pay attention, if we understand all the transitions and everything that's going to happen, we've entered behavior foo, we set pattern A, and then we exit and we set LED pattern normal. Now, we don't know what's happening here. Like that LED pattern normal, maybe that's like instantaneously applied. Maybe it's a asynchronous event and this doesn't actually hurt anything. But then, so very briefly, that pattern went back to normal. And now we've transitioned to behavior bar, and now we've set LED pattern to B. So this transition from foo to bar actually created a small little glitch, perhaps, in that LED pattern behavior. And that's what I want to keep an eye out for. I don't know why we do this as humans, but I've seen this on at least 3 different projects now. And so I just wanted to put this into my tip video so that we keep an eye out for that. So how do we fix this? Well, I'm sure, this is fairly clear and obvious. We just make sure that that state of normal operation sets the LED pattern to normal as it should have on its entry. And now we have a nice clean set of states where each of our states sets that LED pattern only in the entry. So any transition pattern that ends up happening in this product through code maintenance, feature changes, requests, they'll all operate as expected. That concludes 5 tips for unleashing QP on your firmware project. To learn more about QP and how it can benefit the particulars of your firmware project, please check out statemachine.com. And if your team could benefit from some targeted expert consulting related to QP or firmware development even generally, learn more about me at covemountainsoftware.com. Thank you so much. I hope this was useful. If there's any questions, please feel free to send me an email or comment on this video. Thank you very much.